Hello, welcome to Motion Simple Mondays. Today we're going to set up a Xenus Plus servo drive. As many of you are probably aware, the servo drive is one of the three components that is typically used in a motion control system. The first being a motion controller, the second, servo drive, and the third, the servo motor itself. There are certain times that we only use a servo drive and a servo motor. An indexing application would be a good example of this, where we simply move from one position to another repeatedly. In our application today, we're going to be looking at it as part of a larger system. In other videos, we may well set up the drive as a simple indexing drive. For now, let's connect the drive up to the servo motor. Notice in this case, we do not have any communication to the motion controller connected. This will simplify the setup of the drive. The first thing we need to do is connect the main power to the servo drive. This could be 120 to 240 volt single phase or 240 volts three phase. Typically you would want to hook it up to 240 volts three phase. However, in some applications 110 volts may be enough, or in a case like what we're doing here where we're simply trying to get things working, 110 is fine. Next, we need to hook up the 24 volts for the logic to the drive. This powers all of the servo drive except the power that is driving the servo motor itself. If we have this connected, we will be able to talk to the drive and configure it, except we won't actually be able to move the motor. Next, we make the safety connections on the drive. Copley calls this the safe torque off mode. As we see here, we can override this feature for our purposes of setting up the drive by simply wiring as shown in this diagram. This would not be recommended in a fully implemented system, as one of the reasons you use this is to ensure that when you intend the servo not to move, that the servo cannot move. By defeating this, you are removing some of the safety features of the drive. But in our case, since we're just setting it up, this is perfectly acceptable. Next, we will connect the motor power coils, the coils that actually are driving the motor itself. Next, we will connect the motor feedback, which includes the Halls as well as the encoder itself on the motor. Finally, we'll connect the communications cable to drive so that we can talk to it and configure it. We'll start by starting up the Copley application for talking to the servo drive. It will of course remind us here in the beginning that if we hit F12 at any point, we can stop the motor from moving. Next, we will get a series of messages about connecting over the COM ports, the last connection that we showed in our previous section of this video. In my particular case, I was connecting to this drive on a COM3 port previously, but it's not available right now, so we'll go ahead and hit OK. Then we'll go to Tools and Communication Wizards. Since we are talking over serial, we'll do serial ports, and you'll see that I have a COM9 port currently available. Let's add that to the list. We'll hit Next, and we'll leave it at the default baud rate of 115,200 and click Finish. It will once again try to communicate over COM3 unsuccessfully. We'll hit OK, and we'll see that it did actually connect over COM9. We'll go ahead and connect to that drive, and since this drive has already been configured, we'll start from scratch. We'll go up to this basic setup button here, and we'll change our settings. This is a brushless rotary motor. We do have digital Halls. We do want to do Hall phase correction. The motor feedback is in fact incremental as well. We are going to be operating this in a current mode. Again, we're setting this drive up to talk to an external motion controller, which is why we would be doing that. Because we're not using the analog, the plus or minus 10 volt connections to talk to the drive, it's going to be software programmed. Otherwise, we would be using analog command. But we are going to be communicating over the fiber optic network, and because of that reason, it can be software programmed. We are, of course, going to sinusoidally commutate it. There aren't too many reasons why we would trapezoidally commutate. Certainly a motor of this type will be much better off doing sinusoidal. And we'll go ahead and leave the default for this setting here. So at this point, we'll go ahead and authorize all these different changes. Now this gave us a basic setup of how the drive is going to operate. And now we need to go through some of the specifics. The first is the motor feedback. Now, as I said before, I had previously set up this motor. You can see on this tab that I put in the manufacturer and the particular model number. These fields are just really for your own personal reference. It obviously makes sense to put accurate information here, but if that wasn't accurate, it won't have any impact. The other fields in here are all very important because they will impact how the motor is going to be set up and look to the servo drive. Now in my particular case, we can move this over and we can see that we've got these numbers from the catalog. As we can see, this is a Parker BE231FJ. So if we scroll down here, we can see that right about here, a BE231F, we have all of the different information that would come into play here. The motor inertia is listed as rotor inertia. The number of poles is actually listed as the number of poles in this particular case down here. The peak torque is in Newton meters, a unit that is displayed here. The continuous torque again is in Newton meters. The velocity limit is just the fastest the motor can go. You have to watch sometimes in these tables, the speed that they list is not necessarily the maximum speed the motor can go, but it's the speed at which they've gotten all these different electrical values. The resistance and inductance again are usually fairly easy to find because you can see them in units that typically make a lot of sense. In this particular case, we can see them on this diagram right here. The ones that can be a little bit more difficult to acquire are this torque constant and the back EMF constant. It's a little bit simpler to understand where to look for them in a document like this if you have a sense of what these values actually mean. We'll start with the torque constant. This torque constant is the relationship between the amperage that the drive is outputting and the torque that the motor will produce. So I very rarely run across a scenario where it's called the torque constant. In this particular case, we are lucky that it is listed here as a torque constant. You'll see there actually is a torque constant for sinusoidal and trapezoidal in this particular case. Again, not necessarily usually the case. You can see the units that you're using. We've got imperial as well as metric, and since the rest of what we're doing is metric, we'll use the metric values. But the units, if you search for them, are often a better indicator of where to find this information than the name that's necessarily listed here. The back EMF constant is another that is rather difficult to find sometimes. It's basically the voltage the motor would produce if you were not powering the motor, but you say had a large flywheel attached to it and it was coasting to a stop. So in this particular case, we could see that if it was moving at 1,000 RPM, that we would see 15.18 volts. The other thing we can see in here is that the voltage constant is what they're calling it in this particular case. This volts per k RPM. You'll see again we have similar units, which is kind of the tip-off that this is just simply a different name rather than a different value. Like I say, these two are often the most difficult to find. Now that we've gotten all these values put into our table, there is one more tab here we have to be sure that we have actually filled out. In this particular case, it's how many lines there are on the motor encoder. So this particular encoder will have 8,000 counts per revolution post quadrature, but only 2,000 lines are physically on the encoder itself. This is another piece of information that you can find from your servo motor documentation. and sometimes you will get the output number of counts, and sometimes you'll get the lines and the encoder. It's just a ratio of 4 to 1, so if you were to have one, you could always find the other. Once we've clicked on all of that, one of the things that may be a very advantageous thing to do is to save this particular data. You could see here that I've actually saved it previously. The reason for this would be if I was setting up multiple drives and maybe they were in different configurations, I could load this motor data and not have to look up everything on the table again. If we do save everything from the servo drive, it will actually save that information as well, but not as a separate file. So sometimes it's nice to save it as that file. We could also save it to flash. There's really no downside to saving it to flash. It's kind of a good thing to get used to doing on a regular basis. Finally, we want to hit this calculate button. This button will calculate all kinds of other information based on the information that we already provided the tables that we filled in. We'll click OK. It'll ask if we want to set the new value or accept the new values. We'll of course click yes. And it will remind us that we saved it to the motor data flash. Now at this point, the next thing that we should do is set up the motor phasing. So that is this particular icon here. But what I would probably do first is go over to the control panel here, and we could clear our faults and enable the drive, and we should see down here that the amplifier has been enabled. If we cannot enable the amplifier at this point, then other things that we're doing to proceed won't work. So it's important to be able to do that. We can close and we'll go back into the auto phase wizard, and it will let us know that we're going to turn it on and off as we proceed through this. The first step it will have us do is have us move the motor in what we consider a positive direction. So I'll just take and force it to move slightly positive. You could see that the position in my case did count positive. However, there are certainly times that it might look negative. If for some reason you couldn't manually turn the motor, maybe it's part of a larger system or it's simply geared down too much to turn, we could skip. And if we did, it would then later move it in a direction and ask us if that looked like it was positive. That also works well to set which direction is positive in the drive. In our case here, since we already moved it, we'll click next. And then we'll hit start here. This particular step is applying a small amount of current to the motor coils to be sure that it can actually move the motor. Depending on how much load is on the motor, whether it's just by itself on the tabletop or whether it's connected to a larger system, it will change how much current it needs in order to move confidently. If it can't confidently move, then it obviously also has a great deal of difficulty in confidently setting up all of the phasing. You'll see in our particular case here, it's applying a little more than half an amp in order to move. So then we'll click next, and once again start. So the first thing it's going to do is energize one pair of coils to reset it to a position. Then it's going to ask us to watch it to see that it turns one full turn. What we're doing in this process is verifying that the number of poles that we specified and the number of encoder counts per revolution that we specified actually makes sense. If we had put in error, say 2,000 counts per revolution, then you can see how we would get a different number of counts in this test. Also, it lets us know if we did have a scenario where we could see the motor shaft or measure something that one full turn did occur. In our case, we know that it did, so we'll click yes. We'll go next. And now finally we're going to set up the halls on the motor. When a servo motor powers up, it uses the Hall sensors in order to get a sense of which coils to power so that the motor doesn't jump when you first enable it. We'll go ahead and hit start, and you'll see as it goes around the different halls are lighting up, and they appear to be kind of misconfigured right now, if you will. it's gone through and reordered them internally. So if we hit start here again, you'll actually see that it follows now, and you'll see that we're actually very well set up. You don't have to do it a second time. I tend to, just to verify for myself that it was in fact working well. Now we'll click finish. So at this point we've set up our phasing and we've set up our motor feedback. So one of the last things that we have to do is set up the current loop. Now when we are talking to this drive over a motion controller, we're obviously setting up a position and velocity loop. We're only giving it commands in the current loop. But obviously the drive itself has to commutate the motor, and in order to do that we need this current loop set up. So we'll simply click on this box and we'll select Auto Tune. At this point it will go through a series of different moves, make a lot of weird noise and take some time. So we'll cut away, and when it's complete we'll review the results. Okay, so the test has completed. You'll see the different suggestions that it had, and it also of course went through and measured the bandwidth near the end. In my experience, the setting that is the default, this medium setting, is almost always acceptable. I'm sure there's cases where one might want to vary from that a little bit, but we're going to go ahead and accept it in this case because it seems perfectly reasonable. We'll then close out this window and close out this window. Now at this point we should be able to go to our control panel once again and enable the servo drive, and we should be able to click on this enable jog, and as we move positive and negative we should see the actuator move positive and negative. If that is actually working, we can close out of there and we should be pretty much set up for talking to the motion controller. The only other things that would particularly be important on this exact drive would be some of this network configuration, because remember we are going to be talking to this particular drive over a macro ring. In my case you can see the master and slave address is set, the scaling for the amperage is set. You can see how everything is set up here. Typically the defaults on this are pretty much okay, but it can be helpful to see at least someone else's settings to be sure that it's making sense for your application. At this point the drive is set up and ready to go. I look forward to demonstrating in future videos how to do different setups of this drive, as well as motion controllers and other control topics. Until then, thanks for joining.